And zeta of lambda is defined to be the product, I, never been in this business for years, I lambda, lambda t gamma star is defined by this for imaginary part of lambda sufficiently big, where it converges by the counting of the closed orbits I told you about. Then zeta extends meromorphically to C. So as I mentioned last time, this was conjectured by Smale in sort of slightly more general setting. Well, no, it's actually plenty more general setting, but slightly vaguely maybe, in 67, and was proved by Giulietti, so I spelled out the names last time, Giulietti, Liverani, and Policott in this decade, and then Simon Dyatlov and I gave a simple, what to us is a very simple microlocal proof. So I want to make a comment about Nosov flow because yesterday, 2 days ago, my friends Forer and Nonnenmacher took me to task for saying that it's actually, that I said that it's difficult to prove that the flow is a Nosov. And actually, it's very easy, I was told. And then, so I went to Dyatlov, and it turned out that it's even easier than they had thought. And it all can be found in a very easy form in lecture notes on hyperbolic dynamics in chapter 5 on archive 1805 11 6 6. Is it 666? Can it be? I use 666 or 660. This is, in fact, the proof is so simple, I was told that even I could understand it. But I have to say that I meant it really in a less Bourbakiste way. What I meant was that that it's very difficult for a flow to be a Nosov. In fact, most flows are not a Nosov, and this is a restrictive case. And the example that I know best, for which this theorem is already new, is the case of compact negatively curved manifolds. Sorry? It's zero. Oh, okay, sorry. Oh, that's too bad. That's too bad. That's too bad. Okay, so how do we prove this theorem? First, we have a formula which I stated last time. This is a formula which gives a factorization of the scattering matrix of the following form. I was also taken to task by one of my French colleagues that I did not mention that this formula is due to Rouelle. But then I gently reminded my French colleague that Rouelle is Belgian, and they withdrew the objection. But I have no prejudices myself. So these guys here, these zeta functions, actually have an expression in terms of a trace. And for simplicity, well, let me write the general formula. So zeta k of lambda, the logarithmic derivative of this, d lambda log of this, is equal to the trace of, e to the minus I t naught lambda, the flat trace of phi minus t naught star, e to the minus it pk, e to the it lambda d lambda, where this operator here, pk, is the following operator. Pk is 1 over I, the Lie derivative with respect to the generator on the flow, on E0k, which is k forms such that IV, that the forms contract to 0 when you apply V to them. And I will, for simplicity, just talk about k equals 0 case, even though it's just a small technical modification to make it all work for bundles, and then it works for other cases. This trace here, so this is actually a formula of Atiyah combined with Ruel-Thing formula of Atiyah, Bott, and Guillemin around the same time for flows, and these guys for maps. So this is very classical work. And the trace here is formally, it's sort of a formal trace. It's a trace where you take the Schwartz kernel of this restricted diagonal and you integrate or push it forward. And that can be done under some waveform condition, which is always satisfied in this case. So we had the following formal. So I will stick to lambda equals to 0. K equals to 0, in which case this is just P. This is acting now on functions, and this is just application of 1 over IV, the first order differential operator. And then formally, so in inverted commas, that's what we want to justify. We can formally move the flat trace outside of the integral. So, sorry, the integral is from 0 to infinity. Move the flat trace outside of the integral, and then integrate here in lambda, and what you get is 1 over P minus lambda. So formally, this is equal to, and then there's a 1 over I that I forgot, I believe, so that this actually works. This is e to the minus I t naught lambda trace of, well, there's this phi t naught minus phi naught star P minus lambda inverse. Yes. The integrals over T, I don't know why I always write lambda. Thank you so much. So basically, to show now that modulo the justification of this fact, but that's kind of built in once we get enough understanding, to show that this is analytic in all of lambda, what we need to show is that this is meromorphic in lambda with poles that are integers, not poles, with residues at poles that are integers. That's the well, obvious one complex variables. So in other words, we want to study this operator here. And as I mentioned, the meromorphic continuation of this was already to some extent established in the dynamical literature, but was done in a way that sort of microlocally by Faure and Chestrand. And that was done by constructing spaces, weighted spaces, such that this is Fredholm for imaginary part of lambda greater than minus s over c, some constant. So in other words, we'll have some weighted spaces, and what are the spaces? Well, hsg is equal to e to the minus sg L2, and dsg is just a domain and that actually was checked by Faure and Chestrand. That is the honest domain of this operator. And what is G? Well, G is a pseudo-differential operator of maybe just slightly, well, not maybe, certainly slightly bigger order than 0, because its symbol is supposed to be some function homogeneous of degree 0 in psi and log of absolute value of psi. And so, and then this mg has to satisfy the following properties. It's equal to minus 1 near. So let me remind you. So that is the picture I will keep here. This is my picture of compactified cotangent bundle. So that's just like in many previous lectures here. T star of x. This is the boundary. So this is the sphere at infinity. This is the 0 section. And our flow goes as follows. Here is the projection to the K is the map from T star x minus 0 to the boundary, just the R plus action. And then we have these two the dual stable and unstable bundles. And what we do is at the sphere at infinity, we just go from one to the other. And then here we go like that. Well, sorry. Well, you know, it's a schematic picture at best. Huh? Okay. So this is my picture. And mg is supposed to be 1 here and minus 1 here. Yes, sorry? Well, okay. That's right. There's a flow direction. Okay, so I skipped the flow direction. That is true. The neutral direction. It's the characteristic set. So as Simon pedantically points out, I am really I'm interested. Since you see my lambda, I'll just do a modification about this in a moment. My lambda here is sort of fixed, or lambda is in some compact set. I just need to do it for some compact set in lambda. So for me, lambda is really a lower order term. So if I look at the equation p minus lambda square, I'm really looking at the set where p is equal to 0. P is equal to 0 is the set where psi vx is equal to 0. And that's exactly the statement that I don't have any components in the neutral direction. And what is the trapped set, since Simon mentioned that? Trapped set. And this trapped set made an appearance in, well, my sort of general talk and today's Peter's talk. This is where somehow, we have abstractions to sort of global invertibility in scattering theory. Well, what is the trapped set? Well, trapped set is the set of directions which do not escape to infinity. So what is the flow? Well, the flow is e to the I HTP x psi. That's just the lift of the flow in the base to the symplectic to the cotangent bundle. And now you see from the Anosov property that if my psi does not have any components in the neutral direction, this will always go to infinity as long as psi is different from 0. So this means that the trapped set on this characteristic variety is just a 0 section. Okay, that point over there. So this M is supposed to be 1 near K E S star minus 1 near K EU star, and for reasons that I will describe, it should satisfy this condition. So, there is more to it than just this picture, but morally, it's kind of obvious that we can do this. My flow goes as shown. I have minus 1 here, 1 there. Well, I can construct it so that the HP of G is negative, or non-negative, non-positive. Huh? But that's the only condition. It turns out that under these conditions, this is indeed a Fredholm operator. That's a theorem I stated on Wednesday. Now we are going to do something which drives some people crazy. We are going to artificially add a semi-classical parameter. So instead of considering, yes. So how do I prove a Fredholm property? Well, or anybody really proves a Fredholm property. You prove a Fredholm property by adding, well, that's one way, add a compact operator to my actual operator and make it invertible. And if you can do this and also do this for the adjoint, you got the Fredholm property. Okay? So what we are going to do, we are going to consider the following operator instead. P delta of Z, HP minus I Q delta minus Z. So Z, of course, is h times lambda. Now, you may think this is all stupid, but I'll tell you why it's convenient, because what will be Q? Q will be an operator which kills the zero section. And it is convenient to do it semi-classically, because it will, otherwise you have to worry about change of scales. And this way, I can just work in some fixed neighborhood of radius delta. So what my Q is, Q has the properties that, so I wrote it here somewhere, Q delta is an operator of order 0 in the semi-classical calculus. Q delta is the wavefront set, so it's just in the notation of the lectures before, but now a semi-classical wavefront set, so this is the notation of Simon's lecture, is micro-localized to some small neighborhood of the zero section, and the wavefront set of Q delta minus identity intersected with psi less than, say, delta is empty. So this means that near the zero section, Q is the identity, and it lives just near the zero section. So what it does, it puts damping on the trapped set. It kills the trapped set. And the theorem that basically from which everything else follows, both the wavefront set statement and the meromorphic continuation, is the following theorem. It says that so before doing this, I have to do one more thing. I have to change this G to a G which depends on H. So what we do, we now will take a G of H, which is an operator psi 0 plus H, with the semi-classical symbol of G. Now we have to worry what happens near the zero section. So we take some cutoff. So I just won't say it. This chi, sort of like Q, it just lives near the zero section, times my function m of g x psi, log of psi. One of the things about this, semi-classical quantization is that you have to worry what happens near the zero section. Or you have to do things uniformly, check things, blah, 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 but here we just do this. And what happens is that when you use these weights, the spaces as spaces of distributions, they are the same. Because, you just changed this, I multiply psi times h, you just get log of h. This is bounded, so this means it just gives you some power of h. So the norms are not equivalent, but the spaces as spaces of functions are the same. So if I, fix h and get the property of invertibility of this p delta of z, I will have my Fredholm property for this other operator. And so the statement now is that p delta z, actually I just write it like this, that p for h, for z less than, say, some h epsilon, just goes to 0 with h, could do even something else, an imaginary part of z greater than minus s over c times h, because it's already scaled now. So we're working in a sort of h neighborhood of 0 now. We have, slightly larger here, p delta z inverse from this space Hg of h now to itself is bounded by c over h. So in particular, it's perfectly invertible. And the wavefront set, excuse me, the wavefront set h prime of p delta z inverse, I remind you what it is. This is just the semi-classical wavefront set of the kernel, Schwartz kernel of this operator, with the last variable switching sign, reason being that we would like to just have the diagonal in x and psi to be the wavefront set prime of the identity. So that's one way to motivate this. Intersected with the cotangent bundle, you see the wavefront set, semi-classical wavefront set has two components. One lives in the honest cotangent bundle, and one lives on the sphere at infinity. And here I will only make a statement about this. This is contained in the diagonal union omega plus. And omega plus is the flowout e to the t hp rho for t non-negative and rho and on the characteristic surface. So this is the statement. And I want to say that this proof, this follows with perhaps a tiny amount of suspension of disbelief from the estimates that you saw, in particular in the talks by Vashi and Dyatlov. So that is what I want to prove. Well, how are we going to prove it? Well, we're going to prove it using this idea that's been promoted here this week, the microlocalization. We will be estimating pieces of U when I have an equation P delta Z U equals to F. We'll be estimating pieces of U using pieces of F. And then we're going to add them all up, and we'll get an estimate all of U. That's the idea. And the idea will be this, that maybe I wrote it here. Let me just say it in words. When I'm going to be estimating pieces of A, I'll make sure that I will also estimate it only using pieces of F rather than all of F. The reason is that in that way, I'll be able to estimate the wavefront set of U in terms of wavefront set of F. But that effectively is the wavefront set prime of the kernel that gives you the relation. It tells you where the wavefront set of F is taken by the inverse. Wavefront set of F is taken by the inverse of P. Yes. So maybe I wrote it here, but maybe I for the sake of time, I won't go through the details. So I explained last time the general philosophy, the philosophy being that we want to gain compactness by moving from spaces of higher regularity to spaces of lower regularity, and that's how this weight, in a way, is chosen. But I have to say one more thing, which is how we can reduce in the intermediate region, in between the two dots, how we can reduce it to just studying an operator unweighted spaces. Well, it's done by the standard trick. We introduce a conjugated operator. Conjugated operator, well, that's E, and let me get my signs right, SG, P delta of Z, E to the minus SG. And and that is given by, essentially, by the same thing as we had before. I wrote it here somewhere. What we get is P delta Z plus I, the quantization H, quantization of HPG plus H square O of 1, well, let me write like this, psi, and here I have minus 1 plus. So this is, if you like, I mean, you differentiate, and sorry, there's an S here. We differentiate this with respect to S, and what we get is as a leading the derivative at 0 is the commutator of P and G. And that is essentially this term here. And then we have some error terms. Now, this term, unfortunately, Simon really went easy on you guys yesterday or 2 days ago, because he assumed that in such cases, this is actually an operator of lower order. Now, this operator, we all know log is a bounded function, but that's only true in practice, not in mathematics. So this, yes, so it is. So So this is not a bounded function. So it's a little bit worse, no, than what you did, Simon. Yeah, can't have good help these days. So this is recorded. I could get into trouble. So in any case, the thing is that but nevertheless, all that he said applies, provided the imagined term has a principal symbol which is negative. And that is what this condition here guarantees. Okay? So all the theorems of Hermander and the theorems of Melrose and Vashy, and then our theorems about radial estimates apply when we have this extra condition. Yes? Q is even worse, but Q is compactly supported. So I'm not going to talk about, well, I'll talk about Q in a moment, thank you. But Q is Q is not. Q is not. What are you talking about? Q is worse than this. That's correct. Q is even worse, but it has, yes, because this only has an H and log. So it almost sounds ridiculous that you have to worry about it. No, but you see, we know, hey, as I teach my calculus students, a log is a bounded function, but an exponential of a bounded function is not bounded. And when you do these flows, you exponentiate, huh? So we have to worry about this. But the sign is good. Sign is good. So in other words, we can use weighted estimates for this operator equivalent for L2 estimates for this operator. So we can use the estimates that we learned about the other day. Okay, so let me try to go on now with this. And yes, please. What doesn't exist?
The zero section. You subtract it away. Right?
Well, yes, but I want to show invertibility of this, and you see, there is another, huh?
Right. So the reason why you really do semi-classical problem and you have to worry about this, you want to get the invertibility or the register fat.
Yes, that's right. Much nicer wavefront set condition. And also, what's nice here is that I can use the following trick. Okay, let me tell you about the trick. So here is a trick that so what is the standard the wavefront set of U intersected with the cotangent bundle? Let me just write it for some manifold Y. That is equal to the set of all x psi such that there exists, so U has to satisfy some mild-tempered conditions. Let's not worry about that. There exists A, compactly supported, a function in the cotangent bundle, A of x psi, sorry, it's a complement of that set. A of x psi is different from 0, such that if I quantize, take the semi-classical quantization of A, apply to U, the norm of this in L2 is O of H infinity. Okay? And now, if U is independent of H, then wavefront set H of U intersected with the 0 section is equal to the wavefront set of U. Intersected with the complement of the 0 section is the wavefront set of U. So we actually, in other works, we did have some with Jin, we had some estimates of the full wavefront set of this, not just in the cotangent space. But if you want to prove something fast, this is easier to prove. And eventually, our operators that we will get out of this P delta will not depend on H. And hence, we'll be able to just look at the information in the compact set and get the full wavefront set information, which, you know, if nothing else, saves some trees in the sense of less writing. Okay, so now we want to use various places. So I think since I'm a last lecturer, I can use colored chalk. No? We can have different places where we can use our estimates. So the first estimate is, I will put A microlocalized here. But this is exactly the situation, so this is maybe green A. This is precisely the situation that Simon described yesterday. If I take B, not yesterday, maybe Tuesday, Wednesday, we have the following estimate. That, so this is in the green box, we have the following estimate. A U HS is less than or equal constant H inverse B1F plus O of H infinity U in some norm. You see, this is the estimate that is the radial estimate that, as you know, mentioned, really originates in the work of Melrose, where it was sort of a distillation of the estimates in scattering theory, but from a microlocal point of view. In his case, this is HS. And of course, as Simon mentioned, for this, S has to be bigger than some constant, and that constant depends on the lower order terms. And this is where this is where the fact that our M is equal to 1 near ES star is equal to 1 here, we have the high regularity to which this estimate applies. An imaginary part of Z comes into this sub-principal term, and hence this type of condition translates to the condition the imaginary part of Z has to be bigger than minus S over H. Huh? That was this Q. Now the imaginary part of Z is of the form allowed by Simon yesterday. On Friday. So imagine, not on Friday, sorry, on Wednesday. Imaginary part of Z is bigger than minus S over H. You remember the Q conjugated by S, that would give you that you have like S plus imaginary part of Z over H has to be sufficiently positive, but that's this condition. So that is this picture. So this is our foot in the door. This is our foot in the door because we can move on, we can propagate from there. That's what happens in Euclidean scattering as well. Now, case 2, I actually wrote case 0. I will not even write it. I'll just tell you. If I am supported somewhere near the trap set, this is where my flow is bad, because I'm going into it, I'm coming out of it, I can't really control things here. But I have Q there. My operator is elliptic there. I have estimates even without this 1 over H. Elliptic. And, so nothing happens there. I'm not going to even write it. You have an estimate on U localized there by F localized in a slightly larger region because Q is elliptic. So then we have the intermediate regions. So we have some region here, say. I will just write it like this, for instance, here. This is A. A is supported here. Well, and, I will use partition of unity. So this is A is here. Well, then, as was presented on Wednesday, I finally got it. We have some region, whatever, we can do it like that, where this is B1. And then we have some B2, B1 lives here. And then we have B2, which I can't quite draw properly, is here, B2, or B rather, excuse me, to use the notation, such that B controls A. And here we just use the fact that this term and Q have the right sign, hence Doistem ad Hermander apply in this region here. By using those weights, I can now do it. By using the conjugate operator, I do estimates for the conjugate operator, and then they translate to estimates on L2 for the non-conjugate operator, CH minus 1, B1F, HSG, plus O of H infinity U. And this holds, for any S. There's nothing here because the sign is good. Well, S positive, I suppose. Non-negative. And finally, I didn't leave myself enough room there, we get to the sink. So now I have A living here. Oh my. Oh well. Now, in that case, if you recall from Wednesday's lecture, actually, was it in the Wednesday lecture? Maybe not, come to think of it. We have a control region, B, and then again we have some bigger region, B1. The point is, this is more like the situation here. And that is the statement where AU, HS, because now you see my P really has, my spaces, I should say, since my weight is 1 and minus 1, near those sinks and sources, my spaces were just Sobolev spaces, microlocally. Because it's just, you see, I have mg log of xi, so this is just s exponentiation of s log psi, so just psi to a power. That's the Sobolev space. So I should have said that these are the same spaces here. HSG is the same as H minus S, so as HS. Sorry, as HS. Here, HSG is the same as H minus S because my mg is minus 1. So now I have this estimate. Minus S is less than or equal than CH minus 1 B1F H minus S plus B control region H minus S plus O of H infinity. This is the red estimate. Here it is. But now you see, and for this estimate, what we need is that this Sobolev norm is negative, very negative, but it's minus S, and S is very positive, so it is negative, and very much so. Minus S is less than or equal to minus S naught. Again, this depends on the lower order terms, just like in the talk on Wednesday, and that lower term is controlled really by imaginary part of Z, and that gives me the relation between S and imaginary part of Z. So we have these three pieces, and now I know it doesn't look very inviting, this picture here, but you can basically cover the whole thing by either the green one, yellow one, red one, and the silly elliptic one. So you got an estimate over the whole thing. So what we proved, so I can erase the statement here, what we proved now is that U, for U, by the way, as Simon insisted, his estimates were only done, they actually are true for things which are not regular, but we do this for U in C infinity, because C infinity is dense inside of these spaces. And what we proved is that for U in C infinity, U in HSG, if we just use the partition of unity with these different pieces, is less than or equal than a constant over H F HSG plus O of H infinity U HSG, or even better space. But of course, I don't need to explain that I can get rid of this term now. I cannot do this at any intermediate stage. But once I have a global statement coming from these partitions of unity, I get this. So the key here, so this estimate, so this is of course Doistemat Hermander, and this estimate also comes from the work of Melrose, but there have been many refinements, in particular by Dyatlov and Guillermo in the setting of axiom A flows and other applications, and by Hinz and Vashy in the setting of general relativity, and by Vashy before in many settings. We had to do something slightly different here, because unlike in those other works, these sets here, they look very nice as those dots, but they actually neither radial, nor are they very regular. These are very nasty sets. But actually, those estimates are robust enough that more or less the same proofs apply without much change. And once you have correct dynamical assumptions, you don't have to worry about this. And also, as Andras mentioned, so I'm not a specialist, so maybe he will correct me, that this is somehow a form of the redshift. Which one is redshift? This is the source. The source. The source is redshift, and this is black shift, blue shift. Blue shift? Is this blue shift? Hey, I'm no expert on this. So we have this. We have this estimate here. And now, if you look at this, we estimated A only using this species of B here, yes. So consequently, we get out of this a wavefront set statement by making A sufficiently fine. Because you can show, for instance, that you see, if F does not have a wavefront set where B1 lives, you will not have wavefront set where A1 lives. And since I can cover it by those A's, I get my wavefront set statement. So finally, we want to pass to the statement about the wavefront set of the actual resolvent. So we will use this fact. And so I will not worry now about the fact that we have poles, just to keep things simple. And I will translate it all to the case of, so I will now write, so this shows that my operator is Fredholm, which means that this, this is a meromorphic family of operators from ASG to ASG, provided if I translate back to non-semi-classical setting, I have this. And this space contains smooth functions on X, and is contained, so how do I write it? Is contained in the set of distributions on X. Huh? So in particular, we know this has a Schwartz kernel, yes? Any linear map from smooth functions to distributions has a Schwartz kernel, which is a distribution. And this was the theorem of Forchestran, that this distributional kernel has a meromorphic continuation in lambda. And these are somewhat slightly different spaces, but once you stick to this statement, that's what it is. And we would like to compute the wavefront set of this. So let me call this operator, just for brevity, R of lambda. So you see P and lambda, they differ by this. Oh, I erased it. Yes, they differ by this Q, essentially, and H, and so on, huh? Q and H. So now what we have is the following formula for R of lambda. R of lambda is equal to, well, there's an H, but that won't matter, R delta Z, Z being H times lambda, minus I R delta Z, Q delta R delta Z, minus R, so this is, one of those tricks that R of Z, well, you never can escape that one, can you? So this is now my RH of Z, so this is the one with Z in it, huh? Q, but without Q. So if you like, well, let's call it R0, huh? R0 is the one without Q, so let me remind you, P delta of Z is HP minus IQ delta minus Z, and R delta, well, is the inverse. Q delta R delta Z. And what we know is two things. Well, we know we can now study the semi-classical wavefront set of this guy, but of course remembering that it does not depend on H. Huh? But this one does because of Q. And all the terms actually are controlled using this, except for the middle one. Because in the middle one, we have this unknown quantity, the thing itself. However, because of these Q deltas, we know that this is supported microlocally in the neighborhood, small neighborhood of the zero section. So this we know the wavefront set. Here the wavefront set will be just given by those formulae here. So the interesting term is this term. And what is the wavefront set here? Well, we have to apply our relation that we have for this. And basically here, so when we draw a new picture, we have our Q delta. And what it means is that on one side, we have omega plus, so we have anything that flows out of Q delta is contained in this. But here, of course, it's sort of a transpose of this statement. So what we have is anything that flows into the Q delta. And this is where the wavefront set of this guy lives. So I should, I will write it precisely. The wavefront set prime H of this whole thing is intersected with T star x. So we sort of doing it in the easy region. Is contained in I used one of those letters that I learned from Andrzej, but I don't know what it is. It is just the set Y delta of rho prime rho, such that there exists some T and S greater than 0, such that psi of ETHP rho is less than 2 delta, and psi of E minus HP rho prime is less than 2 delta. But the left-hand side not only does not depend on H, it also does not depend on delta. So this means that the wavefront set H prime of R of lambda intersected with a cotangent bundle of x cross x is contained in, well, the things we have from the other pieces, so the diagonal, the flow out, positive flow out, and the intersection of all y deltas. But the intersection of all y deltas are, in this picture, this, which is now the whole stable dual bundle. And this, which is the whole stable one. And we are staying away from infinity, so this means that this is ES star, EU star cross. And this is the statement that I claimed, I didn't write the theorem again, that I claimed on Wednesday for this R of lambda. And now I let H, I remember that this doesn't depend on H. And now I look at the wavefront set, and I can just get rid of this. And I have the statement that we needed. So I have 5 minutes. So I don't really want to, go too far with this, but just let me remind you how the final argument goes. That now, you see, we go back to our formulae. D lambda log of zeta naught of lambda. Well, this is the honest formula due to to Guillemin trace flat of phi minus T0 star R of lambda. So there is, I should say that objections could be made. Sorry, what am I writing here? Excuse me, not yet. E to the I minus ITP e to the IT lambda dt. So this is the formula we had. So this is this trace here of this operator. Now we know, so what happens is that the wavefront set condition in the trace formula shows that this actually is a limit as epsilon goes to 0, e to the minus I lambda 0 t. Can I just cheat? No, I can't cheat really. Not well. I mean, 0 infinity e to the I lambda t trace, the honest trace. So sorry, so I should really put this limit inside, but it's okay, it works. And now the little lemma from dynamical systems that we proved first, the one involving the volume measure of things which are close. So this was a measure of the set of Tx such that T is sufficiently large but less than some big T. And then you look at the set of points at the distance between x and phi t of x is less than epsilon. There is some estimate for that. And using this type of estimate, you can actually estimate this whole expression and get enough uniformity of convergence to be able to move the trace outside. And now, once we move the trace outside, we can actually do our integral. We can move the E epsilon also outside of this and do the integral. And what we get is E epsilon of phi minus T0 star R of lambda E epsilon dt. And E epsilon is some approximation of identity in psi 0. And then you can actually pass, sorry, there's no integral anymore. What am I doing here? It's just this. And now we can pass to the limit and forget this, and we just get the trace of this. But then we are done because, well, we already knew, we actually had to know it when we were doing all these operations, that this trace now, sorry, this becomes now the flat trace when we took the limit. And the thing I didn't describe is what happens at the poles. But at the poles, R of lambda behaves like a resolvent of a matrix. It has some holomorphic part, which satisfies the wavefront set condition, plus P minus lambda naught. So near some pole, J minus 1 pi, divided by lambda minus lambda naught. J, where pi has the wavefront set, these arguments show inside of EU star cross ES star. And now, and this is a bounded operator, it's actually an honest projection on these weighted spaces. So this means when I take the funny trace of this, well, it's funny trace of this, but that's fine. This is analytic in lambda. And now I take the funny trace of this. But this operator is of trace class on the funny spaces. So the funny trace becomes an honest trace on the funny space. But all of those terms, all of those terms can are nilpotent, have some nilpotency in them, and the trace just becomes trace of pi. But pi is an honest projection on a funny space. So this means the residue is the trace of that pi, which is an integer. So consequently, we did prove that this guy here continues meromorphically in lambda, and at the poles, the residues are integers. Hence, this function is analytic, and hence, on some previous board, we get that the Ruel zeta function is meromorphic. Okay, so thank you very much. Yes. That's right. So, but that was, I was kind of, that the point is that, in a way, the picture in Melrose's paper was the same picture, but it meant different things. I would say the Euclidean scattering is more complicated, because even though we deal with operator elliptic, so psi going to infinity is not so important, sort of, at least not immediately, it is nevertheless always has to be handled. And here we only have in psi infinity, and that's where the scattering takes place. That's right. So in Melrose's estimates, this would have been estimates, roughly speaking, not for the x in scattering, but on the Fourier transform of x. The psi variable, that would be the Sobolev spaces. And the regularity in those estimates was regularity of growth at infinity in x. That's right. So we should.